Hello Bobcats. So today we're going to discuss the structure of the atom. Now the atom is made of three basic subatomic particles. Made of three basic subatomic particles. And so we're going to make a quick chart of these particles and some properties of the particles. And in this chart we'll have the name of the particle, the charge of the particle, the mass, the real true mass of the particle in grams, the relative mass of the particle in AMU, atomic mass units, and the symbol that we will use for this particle. And so the first particle is the proton. The proton is found in the nucleus. It has a charge of a 1 plus and a mass of 1.673 times 10 to the negative 24th grams, and it's got a relative mass of 1, and I'll explain that in just a minute, and the symbol I'm going to use for this is a P plus. The next one would be the neutron. And the neutron is also found in the nucleus. The neutron has 0 charge. It has a mass of 1.675 times 10 to the negative 24th grams. Now, this is a very, very small particles, and because they're basically the same mass, they're only off by thousandth of a gram, we would say that relative to each other, they have an atomic mass unit of 1, because they're basically the same mass. And neutrons are this. Now, because the proton and neutron are found in the nucleus and they have relative masses of 1, all of the mass, or 99.9% of the mass, is found in the nucleus. And then we have the electron. And the electron has a negative 1 charge, and it has a mass of 9.11 times 10 to the negative 28 grams. Now, this is over 2,000 times smaller than these other two, so relative to the other two, they have 0 relative mass, or atomic mass units. And we'll write this as E1. And the electrons are not found in the nucleus. They're found outside of the nucleus, orbiting, going around the nucleus. So again, we say that the nucleus is the center of the atom, that contains the protons and the neutrons. And it makes up over 99% of the mass of the atom. Okay, so let's talk about, now that we know some of the characteristics or properties of the subatomic particles in the atom and where they are found, let's discuss the periodic table representation of this. So talk about the periodic table representation of the elements. So if I took and drew something that is similar to the periodic table, we have our square tile on the periodic table, and I'm going to use carbon. So usually at the top, somewhere in the top, you'll see the 6, and you'll see the symbol of the element, and then a number at the bottom with a decimal. Okay, so we need to make sure we identify each of these. This top number is the atomic number. This bottom number is atomic mass, and this is the element symbol. So a few things that we need to understand about this is that, 1, the atomic number represents the number of protons. So that equals the number of protons. Now that's not a hashtag, that is a symbol for number in this case. And we need to understand that the periodic table is arranged in increasing atomic number. Which means that it's arranged by increasing number of protons. Okay. Next thing we need to know is that a neutral atom, one with no charge, in a neutral atom, the number of protons is equal to the number of electrons. Okay. The next thing is the mass number. And we'll talk a little bit more about the mass number. But the mass number is protons plus neutrons. So our mass number is made up of the protons plus neutrons. So it's the mass of the nucleus of a single atom. It must be a whole number. Which means that the mass number is not the same as atomic mass. Atomic mass is something different, and we'll go through that in just a second. And the mass number is the mass of individual atoms. Okay? And the last one we want to talk about on the representation of the periodic table is the atomic mass. So again, we have atomic mass. And it's different than mass number. Atomic mass is the average, or I should say the weighted average. Repeat that. Weighted average of all the known isotopes of an element. And it is not a whole number. And we can also determine the most abundant, isotope by rounding the atomic mass to the nearest whole number. So the most abundant isotope can be determined by rounding atomic mass to nearest whole number. Okay, so we have the atomic number, which is the number of protons, and remember the periodic table is arranged by increasing atomic number or number of protons. We know that a neutral atom, one with no charge, the protons must equal the electrons. The mass number is the number of protons and neutrons in the nucleus, so it must be a whole number because you can't have part of a neutron or part of a proton. And the mass it's the mass of individual atoms, whereas the atomic mass is a weighted average of all the known isotopes of an element, and we can figure out the most abundant isotope by rounding the atomic mass to the nearest whole number. Now let's compare atoms. So how do we compare atoms? In other words, what happens if I change each of the subatomic particles? Okay, so let's look at the first subatomic particle. 1. Protons. The same element has the same number of protons. It's the protons that identify the element. So if they identify the element, if I change the number of protons, you change the element. Now, therefore, we cannot change the number of protons, to be honest. Yes, it does happen in nuclear chemistry, but we do not do nuclear chemistry in general chemistry class. So we will not be changing the number of protons, because if you did, you change the element. In other words, we know that oxygen has 6 protons, or 8 protons, 8 protons, and nitrogen, if I change the number of protons to 7, it becomes nitrogen. So each element has a different number of protons. The next thing is something called an isotope. Now, an isotope is the same element, or isotopes are the same element with different number of neutrons. In other words, if we change the subatomic particle neutron, we get it's still the same element, but it has a different mass. So therefore, different mass number. So I can change the number of neutrons. It stays the same element, but it has a different mass. So let's look at some examples. So if I take carbon 12 and look at carbon 12 and carbon 14. Now this number here after the dash is the mass number. So what we're saying here then is that carbon has, if I look at carbon on the periodic table, or we've already done this where we had our symbol. Remember, if we go back, we already know that carbon is number 6, so the atomic number is 6, so it has 6 protons. It is neutral right now, so it has 6 electrons. And because the mass number is, again remember, the mass number is the number of protons plus neutrons, If the mass number is 12, that means that's 12 minus 6. That means we have 6 neutrons. Now carbon-14, it still has 6 protons, it still has 6 electrons, but now it's 14 minus 6, so it has 8 neutrons. So with an isotope, you can change the mass, but it does not change the chemical properties of the atom. So changes mass, but not chemical properties. So they still behave the same way. They're still the same element, they just have a different mass. Okay, now again, let's repeat. The proton identifies the element, and if you change the proton, you change the element. So we do not change protons. Isotopes are the same element, but they have a different number of neutrons. Therefore, we have a different mass, or mass number. So if we look at carbon-12, carbon is number 6 on the periodic table, so it has 6 protons. It is neutral right now, so it has 6 electrons. And since this is the mass number, which is the number of protons and neutrons, 12 minus 6 is 6 neutrons. If I change the number of neutrons, I have another isotope, carbon-14, but it still has 6 protons because it's still carbon, still 6 electrons because it's neutral, but now it has 8 neutrons. Now, if we look at the last one, we call ions, and ions are the same element, with different number of electrons. So we've changed the number of electrons. So if we change the subparticle electrons, we have ions. Now, and really what we have is a charged atom. So they're no longer neutral. And the types that we have is we have cations. So there's cations. And a cation is a positive ion in which we have a loss of electrons. And since protons are the ones that remain the same, if I'm losing negative charge, I've actually lost, or what I have left over is a positive ion because I've lost electrons. And that would be, usually they are metals. So I'm going to write metals over here. Metal. And so example would be like Na1+. In other words, this started out, sodium has, in this case, we have the number of protons is equal to 11, but the number of electrons is equal to 10. We have lost an electron, so what's left over is a positive charge. Or if I have calcium 2+, the number of protons for calcium is 12 protons, but we have 10 electrons, so we've lost 2 electrons, so there's a 2+ charge that's left over. This happens with metals. Then we have the anions. And an anion is a negative ion, and what has happened here is their gain of electrons. And these are usually nonmetals. Okay, and so for example, if I have N3 minus, that this is where we have 7 protons, so that equals 7 protons, but now we have 10 electrons. So I have extra electrons. Oops, sorry. There we go. So now we have nitrogen 3 minus, which means we have 7 protons because nitrogen is number 7, but we have 10 electrons. Or maybe if I have oxygen 2 minus. Oxygen has 8 protons, and in this case it'll have 10 electrons. It has 2 extra electrons. Now I want you to notice that I write the number before I write the charge, because if I did it differently, if I did it where I write the charge followed by, if you look at this, if I wrote Ca plus 2, it's not wrong to write it that way, but the first thing you think of is that that's a mathematical operation of addition. But remember, it's not addition of 2, it's a 2 plus charge, meaning that we've lost 2 electrons and we have a 2 plus charge left over. So I write the charge after the number so you get an indication that it is really a charge and not a mathematical operation. And the last thing we want to talk about in this video is, the last one is the isotope notation or isotope symbol. So isotope notation or symbol. So if I have, let's say, X here, and that is the element symbol, then we have on top left we'll have an A, and bottom left will be a Z. Now the A is the mass number, and remember, mass number is protons plus neutrons. Z is the atomic number, which is just the number of protons. And then up here there will be some kind of charge on the right if it's charged. If there is no charge, that just means it's neutral. And a charge is the difference between protons and electrons. I don't want to say protons minus electrons or plus, because it all depends on how many did you gain or lose electrons. So it's the difference between the two. So how would we use this isotope notation? Let's do a couple of examples of this. So let's look at, if I take chlorine, and if I wrote chlorine 37 over 17 and I wrote a 1 minus. Now the way we would write this is that this isotope could be written as chlorine 37 isotope, or you can say Cl 37 isotope, or we can represent it as just Cl 37. That's a 37 isotope. This is a charge, and so we can figure out how many protons, how many electrons, and how many neutrons are in this chlorine here, this isotope notation. Now here we know that the number of protons is the bottom number, Z, so that's 17 protons. It has a charge. That means we've gained an electron, and if a neutral one is 17 electrons, when you gain an electron, that means there's 18 electrons, and then 37 minus 17 means there's 20 neutrons. Sorry. So let's say I have isotope magnesium 25. And the way we would write that is that we'd have magnesium 25 here, because remember that's the mass number. Mass number goes on top, and magnesium is number 12 on the periodic table. And if I want to know, in this case we're going to say that this isotope 25 has a 2 plus charge. So we have the number of protons would equal 12, because it's the atomic number is number of protons. Number of electrons, if it's neutral it has 12, but we've lost 2 because it's a 2 plus charge. So when we lose 2 we have 10 electrons. And the number of neutrons would be 25 minus 12, or 13. Now sometimes you will just see an element written as this. Let's see, you might have an element that's just written like, let me give a different color here. If I just see selenium 80. Okay, so if I don't have any other information, we can still figure out how many protons, electrons, and neutrons there are in this element, this isotope, which is selenium 80 isotope, selenium 80 isotope. And we would say that, well, I would look on the periodic table for selenium to figure out the atomic number. So selenium is number 34. So selenium has 34 protons. Now there's no charge written here, and so that means it's got 34 electrons, and then we would say 80 minus 34 would be 46, correct? 80 minus 30 is 50, yes, 46. 46 neutrons. And so that's how we use isotope notation to determine the number of protons, electrons, and neutrons. And remember, we can write this in this with this symbol. We can write it with selenium 80, or we can just write it as Se-80, and that's all representation of that isotope. And so that is atomic structure, basic atomic structure, and that's it for this lecture or video.